All right, we're going to look at specific heat capacity today and see how it can help us calculate how much heat it takes for something to actually change its temperature and how some other factors play into that. So here's the formal definition. Substance's specific heat capacity shows how much heat in joules, joules is our unit of energy, how much heat it takes for 1 gram of something, whatever that substance is, to change its temperature by 1 degree Celsius. Okay, or you can write it out kind of mathematically like this. Okay, so our specific heat capacity is equal to however many joules of energy, how many joules of heat it takes for 1 gram of something to change by 1 degree Celsius. Okay, how many joules of energy per gram per degree Celsius. Okay, so for example, water has a pretty high specific heat capacity. Its specific heat capacity is 4.184-ish. Joules per gram per degree Celsius. Okay, so if you have 1 gram of water exactly, it will take 4.184 joules of heat absorbed into that water to make its temperature climb by 1 degree Celsius. Or vice versa, if you remove, or it loses, 4.184 joules of heat, that 1 gram of water will go down in temperature by 1 degree Celsius. Okay, now, of course, a lot of times you aren't going to be working with exactly 1 gram of a substance or changing its temperature by exactly 1 degree Celsius. That's kind of silly. So in cases like these, we usually make a ratio or a rate or something where we have kind of like something like per gram per degree Celsius. Or like how when we talk about density, we calculate that as how much mass is in a certain amount of volume. D equals M V. So when we calculate density, we take mass divided by volume, okay? And that's telling us how much mass we can cram into a certain amount of volume. And so by definition, you could say it's how many grams of that stuff you could fit in 1 milliliter or 1 cubic centimeter or something like that. But really, it's just how much mass can you fit in how much volume. So to be more general with it, we can write it as how many grams per how many milliliters. Okay, that's it in terms of its units. How many grams of stuff can fit into how many milliliters of space. Okay, so I'm going to erase these ones here because we don't really need them, okay? We might not specifically need 1 gram or 1 degree Celsius to be involved in whatever we're doing, but this just kind of gives us a ratio. How much to this to this? Let's erase this here. Erase this here, okay? You can also think of it like miles per hour. Okay, if you're going 60 miles per hour on the highway, you might not travel for exactly 1 hour of time, but that ratio of 60 miles per 1 hour can give you a way to calculate how far you'll go in a certain amount of time or how long it'll take you to go a certain distance. Okay, say if you need to drive out 45 miles from somewhere, how long will that take you? Or if you drive for an hour and a half, how far will you get? Okay, so we're not really talking about density, so I'm going to erase this so it doesn't get confusing. All right, but this is kind of our setup for specific heat capacity. So this is water specific heat capacity, but depending on the substance, you could have a different number here. 4.184 doesn't seem like a particularly large number, but for specific heat capacity, it is. For another example, copper specific heat capacity is around 0.385 joules, and a lot of metals will have numbers kind of similar to this, very small. In other words, you give them a little bit of heat, and they actually get pretty hot, okay? A small amount of heat for some mass of stuff gives you a pretty decent temperature change, okay? So it would take a lot less heat for 1 gram of copper to raise its temperature by 1 degree Celsius than it would for water. Okay, now this is kind of, odd in how it's written. So we're going to simplify this a little bit. Kind of like, I guess I said we're done with density, but to go back to density, when we talk about something's density, we write out its units, usually not as grams over milliliters like this. We kind of do a little slash. Grams per milliliter. Something kind of like this. Okay? That sort of condenses the unit a little bit more. It means the same thing. This is still dividing. It just kind of puts it all together in one little spot instead of having this big old fraction bar problem we have here. Okay? So I'm going to rewrite this kind of like that. And that's how we're going to see the units for specific heat capacity most often. Okay? So generally, the units of specific heat capacity are going to be written something like this. Joules, per gram, and also per degree Celsius. So since we have it kind of per two different things, we just put them both after the division sign. Oops. Yes, let me change that color because I have it as it's magenta. There we go. All right, joules per gram per degree Celsius. Okay, or usually we just say joules per gram degree Celsius, something like that. Okay, so this is how we usually write our units for specific heat capacity. Okay, so like again, water's specific heat capacity is 4.184 joules per gram degree Celsius, or copper's is 0.385 joules per gram degree Celsius, and so on and so on. And we can use this to go and calculate just how much heat it will take to change something's temperature by oh so much for oh so much mass of that stuff. Okay, so if we want to accomplish that, we have a unit we can use for specific heat capacities. You can look up the specific heat capacity of whatever material you're using. So unless the part of the problem is to try and figure out what the specific heat capacity is, you can just go find out the specific heat capacity of iron, of graphite, of silicon, of neon, of whatever substance you're dealing with, and you can find that number, how many joules of energy it takes to get your certain mass of stuff to change its temperature by oh so much. Okay, so we're going to be looking at how we can use this a little bit more efficiently in math and how we can write out an equation that uses something like this. Okay, so here are the two different ways I kind of wrote this out, either with the unit kind of condensed or kind of laying it out more with the math showing and things like that. But if we want to do some calculations, we need to be able to plug numbers in. How many joules of heat are we using, or how many grams of mass are there of that substance, or how many degrees Celsius is our substance actually changing by. So we need variables. We need letters to represent things like heat or mass or our change in temperature, things like that. Okay, and even our specific heat capacity as a whole. So we're going to replace some of these with their variables and what letters we tend to use for things like heat and mass and change in temperature. So first up, for heat, the unit is joules. But the variable that we use to talk about heat is Q. Okay? Q represents heat, and it's measured in joules. Okay, so if I knew how much heat was being absorbed or released by something, I would plug in that number of joules in place of Q. My grams down here is mass. We tend to use an M to represent mass. All right, so there's my variable for mass. My units there. So however many grams of stuff we're using, we plug in place of m in our equation. Okay? And our temperature is usually represented by the variable T. But I don't really care about what exactly the temperature is. I care more about how much it has gone up or down by. Okay? I want to know how the temperature changes. All right? So typically in science we use a little Greek letter. This sort of triangle here is called delta, and it represents a change in something. So as you go forward in science, you'll see this delta get used for other things too, like a delta M means a change in mass, or a delta V might mean a change in velocity if you're doing physics. A delta, capital T, means a change in temperature. And the unit of temperature we're going to use is degrees Celsius. Okay, so if I have some actual data in the lab, I can start to plug these in for these variables. Okay, so I could plug in some number of joules of heat for Q. I could plug in some number of grams, G, for this mass here, for this M. I could plug in some change in temperature up or down for this delta T here. Okay, now we also need a variable for specific heat capacity. Right. We tend to use C for specific heat capacity. The capacity part is where the C comes from. Some textbooks will use S, like a little S for specific instead, but I like to use a little c. You see this pretty commonly. Okay, so C is our specific heat capacity. Specific heat capacity. Okay, and again, it's measured in joules per gram degree Celsius. Something like that. So all the units we have over here should show up in this unit here. Okay, that's one way to make sure our math works out correctly. Okay, since specific heat capacity is the relationship between the heat and the mass and the change in temperature of whatever is changing, okay, we should have joules of heat and grams of mass and degrees Celsius of a change in temperature in our equation. Okay, to show how something is going on here. Okay, let me add in heat in joules. This is mass, grams. It's changing temperature. Okay, cool. Okay, so now we just have to use this to actually do some math. But the way this is set up is a little bit ugly. It's a little bit annoying. And usually, our specific heat capacity is a number we already have. Okay, it's something that we're plugging in. I go and look up the specific heat capacity of water, and I have 4.184 joules per gram degree Celsius. It's a number I can just plug in. But if I have it set up as that number equals some other stuff I might not know, that's not very useful. I want to be able to plug this in to get it to equal something I don't know. And a lot of times the thing we don't know is heat, which seems kind of weird. It's actually deceptively hard to calculate how much heat is being absorbed or released by something. You'd think we'd have like a heatometer by this point or something, but we don't. We can measure the change in temperature of something pretty easily. We just take a thermometer and stick it in there, and we watch how the temperature goes, kind of before and after. But as far as actually knowing how many joules of energy are absorbed or released, that becomes a lot harder, okay? So most of the time we're actually using the change in temperature, the mass of something, and the specific heat capacity of that stuff to calculate how much heat is actually moving out of or into something. Okay? This is usually the thing that we're solving for. So instead of saying C equals all this stuff, we're going to rearrange this to make it Q equals this stuff. Okay? So we're going to algebraically rearrange this and then use it to calculate some missing things like heat, or maybe mass, or change in temperature, or specific heat capacity. The rest is just algebra from there.